So today we are going to discuss about XLNet, a paper that was published last week from Carnegie Mellon University and Google Brain, and a lot of traction on this paper, and I'm Stefan Egli, will present this paper today. So we will discuss quickly about the context, about the two main approaches, AutoRegressive and AutoEncoding, and how XLNet combine the best of both worlds, and discuss a bit all the mechanisms they use in the paper. So a bit of the context first. Unsupervised learning, it's a rock-solid approach, proven to be useful from context-free word representation like Word2Vec. Then we had the rise of the language models with some example on the slide. And we still have one question. Could language models be useful for mainstream NLP tasks? And a good illustration is the Transformer XL paper from January. It was a big release in the language models, state of the art, really way faster than the previous one. And this paper was rejected by ACLEAR. So there is still this question, could this language model be useful for other NLP mainstream tasks? And we have two competing approaches in language modeling. The AutoRegressive, when I say AutoRegressive, you can think of by LSTM, and AutoEncoding Denoiser, and you can think of BERT when I use this kind of word. And yes, before last week, BERT was the state of the art. So we still have a winner in these two approaches. So we'll discover a bit more these two approaches and see their limitation and how XLNet can help fight these limitations. So this is the goal of the authors, combine the best of both of these worlds and try to have this architecture useful for NLP tasks. So let's discuss a bit about the first approach, AutoRegressive. And as you know, AutoRegressive means you want to predict the next time step using the previous time steps. And you have the mainstream formula to factorize the joint distribution, T1, T2, T3, with a sequential order. What are the limitations? Well, usually when you use this approach, you go from left to right or from right to left. We call that forward or backwards. And when you want to predict a token, you can very well find the dependencies either on the left of the token or on the right. But it's not easy to find dependencies that comes from both sides of the token you want to predict. So you could always combine forward and backward language models and try to capture these dependencies. But this architecture, they never really capture the dependencies from the very bottom of the networks. It's usually at the end of the bottom, at the end of the networks that they combine the two approaches. So this is one of the limitations. Second approach, the AutoEncoding Denoiser, and you can think of BERT. It's based on the transformer, and it's catching dependencies on both sides from the very bottom of the network. But still, we have some limitations. What are these limitations? So maybe a quick reminder on the BERT architecture. So by AutoEncoding, we mean we have a sequence in the output, in a sequence in the input, the exact same sequence at the output, and you add some noise in the input by masking some tokens. And the goal here of this architecture is to predict the tokens that were masked in the input here at the output. So yes, it's cache dependencies, because when you want to predict these tokens, you have at the input token on the left and on the right. What are the limitations? Well, to have this architecture worked, the authors has to mask several tokens as the input. So when you want to predict this token, one of the input here on the right is a mask token. So you are losing one word, and this is limiting the efficiency of the architecture. And the second issue is, let's say you have two consecutive mask tokens, like New York. New York, these tokens are dependent. So if you want to predict New York, it's very important to know that new is the first token, because it could be another two-word cities. And this is something that limitation that generalizes to any dependency between the mask token. So you go for the limitations of the two approaches. And this is where XLNet entered the room. And it's based on an AutoRegressive model, the first one. And it's not just going forward or backward, but it will introduce permutations on both sides. So we will explain that in a bit. Inside, they don't use any LSTM, but again, self-attentions to follow this trend started in the transformer model. And lastly, and we won't dive long into this one, they integrate methods from the transformer XL from 6 months ago, mostly to catch dependency far, far away. So this architecture was a language model, state of the art. So let's start with the first, not trick, but mechanism that is introduced. And we no longer want to go only backward or forward, but when we predict one token here on the top, we want to be able to look on both sides. So to achieve this, we need to define a new order. They call that factorization order. This is the order of the word you are going to predict. So you would start by predicting the word 3, then 2, then 4, then 1. And a sequential language model going forward would be 1, 2, 3, 4. And the backward would be 4, 3, 2, 1. So now it's kind of mixing. The input here, you can think of them as words, like I like New York. And here you want to predict the word new. And in any of these cases, the input new is used. So you use the other context. You also have this mem token here. And this is something just to initialize it. It's at the beginning of the sentence, every time you have a special token to say this is the beginning of the sentence. So for example, here, the first word is 3, and it's the first, so you don't have any other context. So the model only have the init token to look at to find this word. Let's take this example on the bottom right. The order is 4, 3, so now to predict 3, you can use the token 4. So that's why you have this arrow 4 going in, and this init token coming to predict the token 3. All right, so that's it for the permutation language model. And before continuing, I think that's the main point of the paper. And everything that will come next is just to make this logic work, because it's a very simple idea, but we'll see that there are some headaches that the author had to overcome to make this converge. So first is the positional encoding. Why do we need the positional encoding? Well, because we are mixing everything. It's no longer going left to right or right to left. We need to have some positional information in the input, and we'll see also at the output. So good news, this problem was already solved in the transformer. And how was that done? Every input, every embedding here of every word will integrate some kind of sinusoid signal that gives some insight of the position. It's a bit more complex. We won't dive too much. So it's still a sinusoidal signal. Sorry, from the original vanilla transformer, but here they use a relative positional encoding. That's from the transformer XL paper 6 months ago, and it's because when you want to go beyond your current sequence, for example, using the previous sequence or the previous of the previous, you can no longer use an absolute encoding, but you need to be relative to other ones to go further. So not much on that. This is pretty old news. Which sequence to train? So that relate to your question. We have factorial n possible factorization orders. For this example, with 4 tokens, we have 24 factorizations, and it goes wild. So the idea is to sample. So you have random sampling over all possibilities. This is the formula from the paper. ZT is all the set of all factorization orders, the 24 factorization orders. Z here is one of the factorization order, for example, 3214. And here you can find the factorization, as usual, the log probability of, that's the token to predict, the position T of the factorization order, and it takes as input all the previous token before T. What happened to the convergence? Because anytime you add complexity, especially with this size of networks, you make it harder to converge. Well, they decide to only predict tokens with a minimum of context. So which means, in this example, they won't do the first on the top left, and they will maybe not the second one here, but they will only do the third one and the fourth one. Why is that? Even as a human, you would say, trying to predict a word somewhere in a sentence, somewhere in a sequence, knowing nothing, it's kind of crazy to do, and it makes sense that in terms of convergence, it gives some issues. So now the crux of the paper, what they call the two-stream self-attention mechanism. And what is this new problem that requires this split into two streams? Well, we have the position stored in every input, but if you look closely in this simple example, you will see that the model cannot know which position it is trying to predict. It only knows here that it uses the init token. So you would say, well, how we just take the positional encoding from the input here? But the problem is, by doing that, because it's aggregated with the embeddings, you will have to pass also the embeddings of this token. And now the problem is trivial for the model. It will just learn to pass the information of the embedding directly to the output. And your autoencoder is no longer learning anything useful. So that's the problem that leads to this solution. We don't know, the model here doesn't know where, what position it is trying to predict. Oh, sorry. Same slide. So let's go a bit deeper to understand their solution. And here we have very small cells. The representation of H seems very simple on this representation. But here you can think of encoder part of the transformer network. So you will have multi-head attentions, residual connection, layer normalization, feed-forward layer, relative positional encoding, recurrence mechanism. You have a lot here. So passing some information requires to think a bit deeper. And for me, the hardest here to pass some information is the self-attention mechanism. So what do we need to pass and what do we need to remove? We need to keep the positional encoding and we need to remove the embedding content. So here in the same column, you need to block the embedding and pass the positional encoding. Maybe a bit of reminder on the self-attention mechanism used here. And then we will try to see how we can do these two tasks. So self-attention mechanism, you have inputs here on the top, a sentence, thinking, machines, etc. Embeddings. And at the bottom, you have the output, Z1. And the self-attention use three concepts, queries, keys, and values, Q, K, V, all calculated from the embeddings, their respective embeddings. How do you know the output? Well, the output here will be a weighted sum of all the values here. How do you weight each value? You use a score calculated using queries and keys. And it's actually pretty simple. You just multiply the two, you do the dot product of Q and K to give a score that will weight the value. Usually the queries are relative to the output, so output here is 1. So all the queries that we'll use are Q1 everywhere. And the keys are related to the input. So here you use key 1, here key 2, etc. So now you have a score, you multiply by the value, and there's also softmax, and then you get the output. So that's for the reminder. What was the problem again? We want to remove the embedding content and keep the positional encoding. So let's try to build some intuition here on how to do this task. Well, if you want to block the embedding, you need to block the value. Why is that? Well, here you have the value multiplied by a scalar. So the scalar, the multiplication, the dot product of queries and keys, cannot really pass some useful information that will spoil the content of the embedding because it's just a scalar. So we can fairly say that we need to block the values only to solve the problem of blocking the embeddings from flowing from the input to the output. So that's the first thing, we need to block the value. Now we need to pass the positional encoding, and we cannot use the value, so we are left with just queries or key. And because the query is related to the output and the key related to the input, it's more logical that we use the query to pass the positional encoding. A bit complex. This is just to get some intuition of what they are doing. And so again, we need to just block the value containing the embedding and use the query to pass the positional encoding. So yeah, this was just to build some intuition. This is the solution that the paper proposes. They call it a two-stream self-attention mechanism. And we will have one stream named content and one stream named query. So if you look at closely compared to before, now every cell is divided into two. And every left cell will be the content stream, and every right cell will be the query stream. Let's look closer, for example, on the right. We want to predict the first token. We are using token 2, 3, and 4, and the init token. what can we see? The information coming from the word tokens here, 2, 3, 4, they use the content stream, the normal stream. So we have both embeddings and positional encoding. But for the token corresponding to the word we want to predict, we want to block the content. So we have this new query stream, and it's called W because they keep the positional encoding, but they add a vector similar to the embedding just to match the size, and it's just a learnable vector, randomly initialized, that doesn't contain any information. So here W has the same shape as X, but is basically only containing the positional encoding. So this is going to G, the query stream, and this is how the two-stream self-attention mechanism works for training. So at the top here you have a softmax with the good word you want to predict, and then doing backpropagation, we will learn G and H at the same time in all the network. Easy to say. I'm sure for the authors it was very hard to converge with this architecture and find something working. So from the paper, this is more detail on how H and G work. So they share parameters. So J is the query stream, use only the position. H is the content stream, using position, content and position. And you can see that for the query stream, the query comes from the previous J representation without embedding knowledge. So J never gets some embedding knowledge. And the key and value come from everything, from the content stream, so both information of the embedding and the position. But here the difference is that you don't use the last token, which is the one you are trying to predict. But in the content stream, the normal way to go when we don't have this problem, you can use the token you are trying to predict. So that's it for this mechanism. And in the paper, they say that depending on the task, you might not be interested in masking this information, and the fine-tuning can be done only on the content stream, as it's simpler. Right, last component. So we have this permutation language model. We have this two-stream to make it work. And they also use some ideas from the transformer XL. I won't detail too much that because it was 6 months ago described in the paper. But basically you want to capture long-term dependencies, and you will use the previous segments and maybe the next segments to catch some representations, knowing that the gradients will never flow outside of your current segments. You will just grab information but not backpropagate anything. And to make that work, they need to use relative positional encoding. As a conclusion, so we started with two questions. Could language models be useful for an NLP task? And could we get the best of both worlds, AutoRegressive and AutoEncoding? So the answer is yes. There was a lot of spoiler this week. XLNet is state-of-the-art on 18 NLP tasks, including question answering, natural language inference, etc. So great paper. And what's next? My prediction is that, like BERT, we'll have a lot of other paper built on XLNet, trying to maybe make this two-stream architecture better or simpler. And maybe in 1 year, Google Brain and this university will use again $200,000 of TPUs to try everything and merge everything in a paper. Right, thank you everybody for listening.